The next we'll go with azimuthal quantum number. L gives you information about the shape of the orbital. N is pretty simple, right? The principal quantum number is pretty simple. It says the size. Okay, so you went from the number that is there just in front, that is its principal quantum number. Now for the shape. This will give you information about the shape. And there is this concept of L max. The maximum L associated with an N is N minus 1. It might be a little confusing, but just bear with me for just a moment. Yeah.
When you mean shape, do you mean like the seesaw thingy, like how they form?
I will. Yes, I'll go there. Yes, I'm getting there. But before that, let's think about this small thing. That L max is N minus 1. That means for an N, and I also what's the L associated with the orbital S?
0.
Did we write this in class, right? You have it in your notes? So this was 0, this is 1, 2, and 3. This is basically this rule. Now, if we have this, if the azimuthal quantum number of the orbital S is 0, P is 1, D is 2, and F is 3, we can tell how many or which of the orbitals will be allowed for any N. So for example, if N equal to 1, then L max is how much? 0. If N is equal to 2, L max is 1. And if N equals 3, then L max equals 2. This means 1 will only have an orbital that has L equals 0. That means you can only have one S and no P's or D's or F's. This is the thing. 2. The L max is 1. So what are the L's allowed? This and this. So you can have 2 S and 2 P. For 3, you can have a 3S, 3P, and a 3D. Okay? Just an N minus 1. Okay? Any doubts? It's pretty simple, right? Okay, now let's go into the shapes. The shape of the L orbital is spherical. Is this the shape of the S orbital? It's spherical. It could be a perfect sphere, a solid sphere, or it could be a hollow sphere. But it's going to be spherical in shape. Okay? And what's an orbital? When I tell about orbital,
It's a region that electrons can occupy.
it's like a home, right? It's like a home. So I will have an orbital for myself, and that would something look like my office in the university, in here, and my home. So there, if I project it on a 3D space, most of my time I'm there in my office, sometimes in here. There might be some places that I'm absolutely not going anytime. And there are some places where where I can be found most of the time. So the orbital, my orbital, will be the place where there is a decent probability of me being, and my node will be a place where my probability is 0 or close to 0. Like where would you think my probability will be 0? Like anywhere only students are allowed, maybe? Maybe in one of your fraternity homes. So my probability there is 0, so that's my node. A similar concept with electrons. The shape, so if you have an x, so whenever we are talking about shapes, we have to orient ourselves in the space. So the shape of the s orbital will be something like this. Okay, so this could be a sphere, a solid sphere. This could also be like a hollow sphere, in which you just have the metal outside and just the hollow inside. Okay, now this place, so we'll get into the concept of node, but imagine that there is a hollow sphere. Okay, so that hollow is the node, because it's hollow because the probability of the electrons being in the hollow is 0, and that's why it is hollow. So anything that is hollow, that means the electron is not going there. It's like a probability density kind of a thing. It's like if you take a snap, if you take an image of the orbital throughout its lifetime, and superimpose all these. So what you will get is electron is somewhere in here, it's moving, so this kind of takes the shape of a sphere. So this is the orbital, and this is the 1s orbital, which is the perfect sphere. If you go to 2s, this 2s is this. So it is only found in here. So the middle part is a node for 2s. So 1s has no nodes, but 2s has a node. Okay? Think like that. But if you're getting confused, forget about the node, just think the shape. It's spherical. That's it. It is just spherical in shape. Now, in how many ways can you orient a perfect sphere? In just one way, right? If you have a perfect sphere, will you be able to tell me the difference if I just twist it by 90 degrees or whatever? You won't be able. So that means this thing has only one orientation. So s orbital has one orientation only. And the third quantum number deals with the orientation. So this is called the magnetic quantum number, which is the third quantum number. Now, what is the magnetic quantum number of S? Or how many magnetic quantum numbers will S have? One, because the sphere has only one orientation. So whatever that magnetic quantum number will be, there will be only one of those. Okay? Keeping that in mind, let's move on to the p orbital. The p orbital has a shape like this, and it's called the dumbbell shape. The dumbbells that you use in the gyms, think like that. But it's like a balloon pinched in the middle. Think of that, I will show you in the next class with some PowerPoint presentations, like the actual shapes, because it's very difficult for me to draw. Think of it like a balloon, but you pinch it in the middle, so it forms a lobe here. It forms another lobe here. Okay, that's the shape. So the azimuthal quantum number of p orbital is 1, of s orbital is 0, but how many ways can you orient the p orbital? Primarily 3 ways. You can orient it towards the x-axis, so this becomes a px, or you can orient it across the z-axis, so pz, and you can orient it about the y-axis, so this becomes a py. So there are 3 orientations possible for p orbital. So how many different magnetic quantum numbers will be there for p orbital? 3. Because it's just the number of orientations. Now, the d orbital, it gets a little complicated. This is called double shaped. It has this form. So it is, you can see this is becoming a little complicated. Just passing the sheet around, just see how it looks, okay? I'll show this in the next class, in the presentation. Now, the d orbital now can have 5 orientations, and I will show you the 5 orientations. There will be dxy, dyz, and dxz, dx square minus y square, and dz square. There are 5 orientations. Can anyone guess how many orientations does f orbital have?
7.
Why? Why did you guess? How did you guess? You're right.
It goes up by 2?
Sorry?
I said, well, P was 3, D was 5.
What else is associated with P that has 3? What else is associated with D that is 5?
Is it half of how many electrons can take?
Yes. It's the number of boxes. The number of orbitals, right? Suborbitals, if you may. Now, quickly, I'll repeat a little bit of this in the next class. But S, P, D, S, P, D, and F. These smaller boxes are actually representing something. What is it representing? If we can just count those, they're representing the magnetic quantum numbers. So just S has magnetic quantum number of 1. It's just 1 orientation, and that's why it has just 1 box. P had 3 orientations, and that's why it had 3 boxes. D and F, 5 and 7. Now, the L for S can go right? And the M's, the magnetic quantum number, go from minus L to 0 to plus L. That means for S, what is the L? 0. So the M can only be 0 because there's only 1 orientation. So this becomes a 0. For P, the magnetic quantum number becomes minus 1, 0, and plus 1. numbers are just the magnetic quantum numbers. And these are representing the different orientations that exist in the D. So there are 5 orientations, and each orientation has a number associated with it. That's it. So you can imagine this could be px, py, pz, xyz. It doesn't have to be -1. It's just a convention. You can have py as -1, 0. It's just that. Same for d's. So you can have dxy, dyz, dxz, dx squared minus y squared, and dz squared. Oh, I did not take the attendance. Sorry. Can you quickly, just a name would be fine today. All right, does that make sense? The last one, and in the last 1 minute, is a spin. And spin is easy, it's either +½ or -½ for the electron that is coming in. So this is a +½ this is a -½ So we got 4 quantum numbers associated with any electron: the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. For example, for 11, if this is 3s1 is the last one that is entering, so 3s1 will have 4 quantum numbers associated with it. The first quantum number is principal quantum number. The second quantum number L is, for s it is 0, m is again 0, and s is +½ So for every electron, for any electronic configuration that you do, you can have 4 quantum numbers associated with that electron. And no 2 electrons will have same set of 4 quantum numbers, and that is called Pauli's exclusion principle. Okay? Cool. So we'll leave it at there. Sorry for keeping you 2 minutes past, but thank you so much. Next Monday, the assignment set is due. Okay?